Welcome, I'm Samuel Holt, and this is Neural Laplace Control for continuous time delayed systems. This is joint work of my excellent co-authors Alihan, Jiaji Hao, and my supervisor Mahela Vandershaw. What is offline reinforcement learning? Let's start by looking at online reinforcement learning, where typically we have an agent that gives an action to the environment, and then it receives a new state and a reward based on this action. Now, this is normally costly and requires a costly trial and error approach to learn, often requiring millions of interactions with the environment. However, this is often unrealistic, as we might need a very accurate simulator of the environment, or one may not exist in the real world. Whereas in the real world, we often have environments where we have collected data set of previous state action trajectories of previous agents interacting with the environment, and we wish to leverage this previously collected data set of state action trajectories to then learn an agent to interact with the environment firstly. In this case, we look at model-based reinforcement learning methods that learn a dynamics model of the environment and use it to plan. In this case, we can train a policy or use something like model predictive controller to plan. We look at the first method to approach more realistic environments of continuous time environments with delays. First, let us look at continuous time environments in this setting. So these are often described by a delay differential equation with a constant action delay. These principally, actually the dataset trajectories of the state and the action can be observed at irregular time intervals. As well as, these actually have an unknown action delay inherent to the environment or the environment dynamics. We also note that actually an unknown fixed action delay is the same as an unknown fixed state delay, and this has been proven by previous works. Now, this is really applicable to more realistic environments. For example, autonomous driving braking systems, where it actually requires a small delay, action delay, for the hydraulic system to actually kick in and give desired deceleration. And crucial understanding of this is really key for accurate control of these high velocity systems. Satellite control, where the Earth and satellite actually move and causes observations, which are regular in time and also unknown fixed action delays. Healthcare as well, where we actually don't observe the outcome of a medication on the patient instantaneously, and instead we observe a delayed version of it. As well as business, more realistic environments, where we don't actually measure the outcome of actions taken immediately, and hence they're delayed. In this method, we propose Neural Laplace Control framework that solves these types of environments. Now, it's a continuous time model-based offline reinforcement learning method that combines a Neural Laplace dynamics model with a model predictive control planner. This gives the immediate benefits of being able to learn from an offline dataset sampled with irregular time intervals and has an inherent unknown constant delay. We actually show that this provides more accurate dynamics model for varying continuous time with prediction at a future time, enables planning at a longer time horizon using model predictive control, using a fixed amount of compute, and able to plan at the same time horizon using less compute as well. And doing these gives great sample efficiency and achieves state-of-the-art performance of offline reinforcement learning performance. So the method works in principally two steps. One, learning a dynamics model in the environment, and then two, using this dynamics model with a model control planner to plan and take action trajectories. Firstly, the dynamics model, we extend the Neural Laplace model to what we call Neural Laplace Control, which takes the action history input as well as the current state and represents this in the Laplace representation and models the future expected trajectory. This principally consists of three components: an encoder that learns to infer and represent the initial representation of the current state action trajectory up to a time t. Two, a Laplace representation network that learns to represent solutions of the state trajectory in the Laplace domain conditioned on the input state trajectories. And three, an inverse Laplace transform algorithm that converts a Laplace representation back to the time domain. We also note that Neural Laplace Control is preferable for nonlinear dynamics, as nonlinear delay differential equations can be solved explicitly in the Laplace domain through concepts like the Laplace domain decomposition method. Firstly, The encoder, we use a encoder to use a fixed history window of the action, where omega in this case is greater than or larger than the unknown action delay which we wish to learn or infer of the environment. And we take the current state as well. Here we use reverse time-gated recurrent neural networks to create this representation of the initial condition, and we concatenate the two representations together. Using this representation, we actually put this into a function modeled by a neural network to describe the Laplace representation of the current trajectory, such that when we take the inverse Laplace transform of this Laplace representation, it approximates the future trajectory well for future time. Now this Laplace representation, as previous work has shown, often involves singularities. Therefore, we follow Neural Laplace to use a stereographic projection onto a Riemann sphere to mitigate this. This principally looks like this, where we translate any complex number into a coordinate on the Riemann sphere using this stereographic bijection mapping. And we model the neural network on this sphere itself, where the neural network is a feed-forward neural network represented as G here. Once we have the Laplace representation, we can use the inverse Laplace transform to compute the predictive values of xt using a numerical inverse Laplace transform algorithm, where we use the inverse Fourier series inverse Laplace transform algorithm. Now these inverse Laplace transform algorithms are numeric methods which actually take two steps. So we give them a set of time points we wish to estimate the future values for, and they give us query points, and then we give these query points into the algorithm. The biggest benefit of this is that we can actually evaluate at any future time of the Laplace representation, and really because the Laplace representation is independent of time once learned, therefore it only requires one pass through the network to predict at future time, whereas neural ODEs require many steps to predict a very far future time horizon, which gives us performance benefits in computational efficiency, as we'll see in a minute. So Neural Laplace Control, it's a framework that can use any model predictive control planner. Principally, we use the model predictive control planner of model predictive path integral. This computes a discrete action sequence up to a fixed time horizon, where each discrete action interval is defined as a small delta seconds long. Principally, if we look at the related work, we see that Neural Laplace is the first method for offline RL where trajectories both have irregular samples in time and have a fixed unknown constant action delay. The results across the board show that Neural Laplace Control achieves state-of-the-art episodic reward performance across 3 standard continuous time reinforcement learning environments, achieving near expert policy performance when using only learning dynamics model from a dataset of collected trajectories that is irregularly sampled and has an unknown constant action delay. We also performed inside experiments, and we can see that Neural Laplace Control can learn a good dynamics model where it can correctly learn a good prediction of a future time input, whereas other methods like neural ODE methods struggle to do this. Similarly, Neural Laplace Control can also learn correctly the delay environment dynamics, where actually for various delays, the forward prediction error looks similar. Similarly, we can plan with a longer time horizon using a fixed amount of compute as well, which is beneficial, where we see the increasing horizon on the x-axis, and we see Neural Laplace Control achieves good performance over a longer time horizon whilst keeping the fixed amount of compute. Whereas neural ODE methods actually scale linearly in the amount of compute, which provides them difficult for use with model control planners in this setting. Similarly, it can also plan for the same horizon using less compute, being able to predict a good action which still achieves quite high-performing policy performance in much less time. And also, we show that Neural Laplace Control is also sample efficient. in this case learning on the cart pole environment from just around 10 seconds of interaction time, achieving a sufficient policy performance. To summarize the contributions to this work, we propose the first practical framework, Neural Laplace Control, for environments that are continuous in time and have constant unknown action delays. We can achieve state-of-the-art near-expert policy performance. We can correctly extrapolate to longer time horizons for the dynamics model. And it is computationally efficient for predicting the next state at a longer time horizon, therefore making model-to control feasible for longer time horizons for a fixed compute budget. We hope this work provides a practical framework to advance offline reinforcement learning methods, which are immensely useful applying to real-world environments.